My name is Florian Weimer. I work for the Red Hat Platform Tools team, and I want to talk about a new TLS allocator for the GNU C Library. This talk is probably going to go for like 35 minutes, but I've got the next slot as well, so hopefully it doesn't matter if I overrun a little bit. So I want to talk about the thread local storage allocation task and what we currently do in glibc in terms of different TLS types and different allocators. Then I want to propose a unified initial-exec TLS allocator for a certain TLS type, and then a new global dynamic TLS allocator. None of what I'm going to cover in this talk is actually really new stuff. These ideas have been floating around in the community for a long time, and Sabaj Nudge has written up some of the ideas in two bugs in Bugzilla that I mentioned there. So what is the TLS allocation task? glibc needs to provide thread local storage for up to 2 applications. And thread local storage has a couple of different applications. The first one is a performance optimization, because if the storage area is thread specific, then you don't need any synchronization accessing it because it's private to the thread and you don't need to use atomics or locks. So there's a performance benefit. Then another benefit is, another application is that sometimes you have legacy APIs that have implicit global state and you want to lift that into a multi-threaded world. And then it is tempting to say, okay, we're not changing the API. We are just going to use thread local storage for the global state. And the other option that you have is that you deliberately design a new API that depends on thread local storage for programmer convenience. On Linux, the access is somehow routed through the thread pointer. We do not have thread-specific page tables, for example. So the memory is a linear address space. Every thread sees the same address space. With one exception, there's a kernel page that is different, but in general, the page tables across the threads are the same. So we need to have this special thread pointer. How that is materialized in the implementation varies from architecture to architecture, and the access to thread local storage goes through the thread pointer. There are various ways to construct thread local storage, and we have a kind of like 4, 5, 6 categories of that are somewhat interrelated. The simplest way is that you say, okay, here's my thread control block. The API says, okay, at this address in the thread control block, there is my thread local storage variable for this specific purpose. We have things like split stack support, stack protector that use that model, or hardware capability dispatch flags. Then there's local exec TLS that is for the main program. Initial exec TLS is for shared objects that are loaded first with the main program. Then global dynamic is for use with DL open and shared objects. And then we have POSIX thread-specific data, which is using the pthread key create API that is also thread-specific storage. And there are different constraints for each variant. So there are trade-offs, performance, capabilities. And we have certain choices made in glibc as well that are not constrained by the mechanism as such. For example, for global dynamic TLS, we do lazy allocation on first access, which means that any TLS access can fail if we are out of memory, for example. And we also have an implementation for POSIX TSD that has a really low number on the number of keys you can allocate, but that is not constrained by the interface as such. There are two major categories for static TLS. TLS. There are two major TLS types. Static TLS is anything that has the same offset from the thread pointer in all threads in the process. So you have a variable in the first thread, a TLS variable in the first thread always has the same offset from the thread, from the thread pointer as TLS variable A in another thread, and that is constant across the process. For initial-exec TLS, this varies between executions. So there's some runtime overhead because you have to determine the offset. That is it's just a constant load from constant data. Then for the TCB ABI and for local exec TLS, it's a fixed offset that is basically baked into the instruction stream, and you can't change it, and it's constant even across different processes of the different executions of the same executable. The other large category of TLS is dynamic TLS, which has a completely arbitrary address in every thread. That means you can do an arbitrary amount of DL opens, because if they use global dynamic TLS, they just get the memory from somewhere, and you are not constrained. If you use initial-exec TLS with DL open, then eventually you will run out of the pre-allocated space, because we cannot relocate the thread pointer. That has to be in the fixed space, and eventually the initial allocation for that is full, and then you can't load in anything anymore. So that's the reason why we have global dynamic TLS, that we can work around that kind of restriction. There's a significant cost in the current implementation to using global dynamic TLS, so there's a trade-off to be made, which variant you want. And POSIX TSD, thread-specific data, is very different from everything else. The API is completely mediated through function calls, and there's no way to get an actual address of the data. You only can copy out a pointer value that is stored at that place, and that's it. So it's also very dynamic because there's no constraint on where it is stored. So this diagram shows how the current first variant of TLS allocation works, how the things are laid out in the process. So we have the thread pointer for each thread, and it points into at the start of struct P thread, and inside struct P thread, we have the thread control block at the start. And in this particular variant, the local exec TLS is in lower addresses directly below the TCB, and then we have the initial exec TLS at a variable offset from the thread pointer at even lower addresses. And it's the job of the dynamic linker to place the initial exec TLS in the right place and make sure that the entire area is large enough to store everything. And the complications start when we go and look at global dynamic TLS. So there's a dynamic thread vector for each thread, and this can be reached through the thread control block. There's a TTV pointer, and the dynamic thread vector contains, for every module, every thing that has been loaded with DL open or any shared object that has been loaded, contains an entry, a module entry, and that module entry points to the start of the TLS block for that module. And also the initially loaded objects also get their own module IDs, so that they can all be addressed through that global dynamic interface. And the global dynamic TLS access is based on GNU TLS descriptors, so that is the thing in the lower left. And those contain a module index, and for technical reasons that have to do with ELF symbol resolution and stuff, there's also an offset in the module that is not constant. So sometimes, yes, global dynamic TLS has a constant offset in the block, but it can also be a variable, because if you have a symbol reference to an ELF symbol, and it is not guaranteed that even if you define that TLS symbol in your shared object, that it will be bound at runtime. It's bound to the same definition that is in your shared object. It could be in a different shared object that has priority over you. And therefore, the offset is not even constant there. And yeah, if we have the fully global dynamic mode, then you can see that at the lower right side with TLS5 and TLS4, these two TLS blocks are completely arbitrarily allocated somewhere in the address space, and we always use malloc for all of this. For the lower half, this is allocated by malloc. And yeah, these data structures are also dynamically allocated at runtime when we do the first TLS access. Any questions at this point? Questions? So this is the first currently implemented variant. There's a second variant that has the same elements, but it is, I don't know why it keeps blanking. So this is basically the same variant, the same diagram, but some aspects are shifted around. And this approach is particularly useful to certain risk environments because you don't have like two. This one has like has access below the thread pointer, and then it gets more complicated in certain cases with alignment and stuff. And this one solves these issues, but there's a complication that the link editor has to compute the gap between the TCB and the local exec TLS block. But otherwise, the initial exec TLS placement is just at higher address. It was at lower bit address before, so it's just flipped around. And the DTV mechanism with the dynamic thread vector for the global dynamic TLS, that is pretty much the same. Yeah, the thread pointer points to somewhere in this range. For RISC architectures with limited instruction displacement or limited immediate operand sizes, sometimes they use a biased thread pointer so that when you go negative with the offset, you can actually use that to go to the TCB. And because the negative offsets wouldn't be useful otherwise. But not all RISC architectures do it this way. So these are the things as they are implemented today. And we are not entirely happy with this because the multi-level indirection for the global dynamic TLS access is slow. The implementation, because it makes lazy allocations, can fail at any time. And there's no error reporting except for terminating the process, and that's not very satisfying. And it's also not async signal safe. And that is a specification violation. TLS access has to be async signal safe. But the other thing is that the two diagrams are slightly different, and we have different code doing the allocations for them because the layout is slightly different. We actually had 4 different allocators. We recently get this down to 2 because we unified the statically linked executable code with the dynamic linker code. So that's already an improvement. And what I think we could do is that we just identify the gaps in both layouts and give the allocator this information, and then the allocator uses a uniform algorithm to allocate for both types of layouts. And this is, we can only change the allocation algorithm. We can't really change the placement because the initial-exec TLS placement is determined by ABI. We have the flexible offset, but we have to accommodate the fact that this offset is constant across all threads, so there's not much we can do. But we can still use one allocator and tell them tell the single allocator where the gaps are. And we can also use some of the incidental gaps that are marked with the part and parentheses. We can use those as well. Currently, we don't always pick up the slack space between allocations, or that are just there because of layout and alignment requirements. So the one thing to keep in mind is that because we can unload shared objects by calling dlclose after they have been opened by dlopen, and the order of dlclose and dlopen calls are not exactly the reverse, then it might happen that we create gaps. So we need to reserve space up front so that we can keep track of the gaps. Otherwise, we can't be sure that we can allocate that memory later when we call dlclose. And we can over-allocate and use mprotect as necessary. That is sort of complicated in the count allocator. And when we allocate the initial TLS exec, we need to zero, otherwise initialize existing memory on existing threads when this allocation happens through dlopen. But this is something we already do in the count allocator. If we have this allocator, what we can do is we can also start moving this stuff to the entire static TLS area. We can move that to a separate allocation, and currently it's at the top of the stack, which is convenient for some purposes. It may be more efficient from a TLB pressure perspective, but the disadvantage is we can't really go wild and say we want to have 64K. I don't know why this is.
Or at least once I saw something about temperature.
Okay, this is not something I control. Yeah. Okay. So we can reserve more address space if it's a separate allocation, because sometimes allocations sometimes applications bring their own user stack, and if we take like 500 kilobytes out of a 1 megabyte stack, that the application might not expect that. So if we keep that separate, then we can go allocate more, reserve more things up front, and then we can use more of the initial-exec TLS variant. And the other thing is we can do this on the main thread only, the over-allocation, and then learn about the actual initial-exec TLS usage of the application as it calls dlopen. And that could also help to improve compatibility with the scenarios where we are not able to size the initial allocation size correctly. For example, if you're using the auditing feature of the dynamic linker. So for the global dynamic TLS data structure, the idea is to get rid of most of the indirection as far as possible. And the key insight here is that instead of having a module-specific pointer that points to the start of each module, we have slices of TLS that contain multiple modules, and we use the offset that we already have to tell which to assign the right place for each TLS variable. And if we adopt an exponential sizing policy for the slices, then we only need very few of them. There are 21 slices here in this diagram, but maybe we need 24, maybe we need 15, I don't know. But the size of the array is not part of ABI. We can tune this later on as we gain more experience with this approach. And the slide 0 is actually the static TLS area. So we have a unified way for accessing all types of TLS, like we had before with the global dynamic interface. but this one has fewer indirections, and this also doesn't have the lazy allocation aspect. So the idea would be to allocate these upfront on at DL open time for existing threads, or on POSIX create time for new threads. And because we don't do lazy allocation anymore, so every thread immediately uses all global dynamic TLS as it is defined by the application. But in most cases, if it's zero initialized, then we still use memory overcommit from the kernel. So it is not, you wouldn't get an immediate failure. So even if you have a gigabyte object in TLS, not that you should do that, but if you had, then that still would be overcommitted by the kernel. And there wouldn't be much difference to the current lazy allocation approach. And apparently the slides stopped working altogether. So the slice area, the array of pointers to the slices is fixed size, and we can put that into struct pthread. That makes it very efficient to access from the thread pointer. And the key change, as I said, is that each TLS block is no longer in a dedicated allocation, but shares it's sliced usually with multiple other DSLs. For GNU TLS descriptors, we can specialize them per slot. That is particularly desirable on x86-64 because the ABI is a bit difficult there, and we only have one register to work with, which is not a lot. But if you specialize it to each slot, then it is possible to use that efficiently. And the encoding for TLS, traditional TLS descriptors and the TLS get address function needs some research. I don't quite know what the backwards compatibility impact is there. We have flexibility there to try different approaches. I assume that's the 5-minute warning. And in the slices, we can reuse the initial TLS-exec allocator, the linear TLS-exec, the linear static TLS allocator. And if we run out of space, we just start a next slice with double the size and double the alignment so that we get the exponential growth policy. As an optimization on new threads, we can use a single mmap call to get the storage for that. So we don't have to do like separate calls if we don't want to. And we have a couple of synchronization changes because currently we have this elaborate scheme using the generation counter and the synchronization scheme involving the DTV array to make sure that when we access TLS for the first time, it is synchronized with the dynamic link of data structures that define its initialization patterns and stuff like that. And that is really complicated. Not all of that is going to go away with the new scheme, but we only have to do it once, or once at thread start and once at thread exit. So essentially, the slow path from the global dynamic TLS access will be completely gone. This has been tried before, and what didn't work back then was the sanitizers broke because of this, because they need to track the allocations, need to see the pointers in them, and if we just do mmap on the side and they are not aware of that, then leak detection, for example, doesn't see the pointers anymore or the thread. And if we reuse those allocations between threads, then it looks to the thread sanitizer as if there has been an unsynchronized access between two threads. We can solve this if we use malloc or aligned alloc if we detect that the address sanitizer is in the process. And eventually that probably the address sanitizer should be more tightly integrated with glibc so that these problems are slightly mitigated. And that's it. Questions? Arjun? And do you have, can you take the microphone?
I don't, okay, yeah, I can hear myself. The local exec, access to it got slower, right? From, I mean, will get slower, or, because if I remember correctly.
Local exec is completely controlled by API. So if you look at this here, this is, there's nothing we can do about it because this is fixed instruction sequences in the object file. So this doesn't change at all.
And then can you move to the new scheme?
Yeah. So the new scheme, you can still use the old. So the S0 pointer is only there for like completeness, that you've got a uniform access.
Sorry, that's what confused me. The S0.
Yeah, sorry about that. It's, can you?
In this new version, thread pointer is also set. It doesn't appear in this scheme.
Yeah, there's a set pointer that, that it points somewhere. So it could be like, if you've got a RISC architecture, it could be biased and then it points somewhere else. So if you didn't do that and your bias is 0, then that is actually good for the new scheme because the slot array is reachable with a negative offset. That is really nice. But if you like, if it is not reachable from the thread pointer, then you need to have an additional instruction to get a larger displacement.
So one thing that is not clear to me is you said that as an optimization, you can map the whole new data structure, including the struct pthread plus the dynamic TLS. But in the next slide, you said that the idea also is to use malloc and replace with aligner lock for libtcn. So what's your current idea to allocate for new thread?
We would use mmap, so because it's going to be like 64K at least for the first global dynamic allocation. And if you start using that, then, I mean, why use malloc for that?
Yeah, I mean, because it does not solve the libtcn problem to track the internal metadata that we are allocating for TLS.
Why wouldn't, I mean, the thread sanitizer still scans the allocation around the thread pointer, so that would be enough, I believe.
Yeah, I'm not sure. Yeah.
And we would only use the malloc and the aligned malloc fallback in case that we detect the address sanitizer as active. But ideally, nothing of this should be necessary when we teach the sanitizers about the new way of doing things. Okay. I've got a bonus slide about pthread create. So you can see is there any further questions? No. Okay. So the main TLS access is just this line anymore, and we have currently we have 200 lines of code for the fallback path. So that's not good. Okay, thank you.